Okay, doesn't look like it. And just to reiterate, the dynamic is a lot different in these sessions. So usually I would pause on every single step of a question, allow you guys to solve it, go over why you think that's the answer, really kind of get in depth into the details of certain questions. For these, not so much. It's going to be kind of me just doing the problem how I would do it. Let's say if I was still taking Physics 50, rather than having you guys explain it to me. But while there will be chances for you to solve the problem, I will give you time and allow you to solve the problems. I'm not going to take it step by step like I usually do. It's going to be kind of me just showing my steps, how I would do it. Just sort of more of a tutorial type thing. So are there any questions before we get started? Again, you are limited to the chat if you want to ask questions. All right, so just remember, please avoid turning on your cameras, and we can get started with the session. So here's our agenda. We just did a short intro for the past few minutes. Majority of our time is going to be done with practice problems, and then like usual, and then last 5 minutes we're gonna have some closing questions, opportunities for you guys to ask me things about the problems from today, about the class, about whatever, anything that you have questions about. So let's get started, and let me share my screen. All right, let's get started on this first question. And it has to do with work. So today's focus is going to be work and kinetic energy. Two pretty important topics for this class. For the next couple, at least, a couple of weeks, your big focus is going to be on the various types of, energies, mostly gravitational potential and kinetic. And then as we move forward to potential, conservation of energy, this is going to be a big focus. I really want us to get a lot of practice in with this type of stuff. So the question states, you have a bullet moving at a speed of 153 meters per second, and it passes through a plank of wood. After passing through the plank, it has slowed to a speed of 130 meters per second. And another bullet with the same mass as the first one passes through an identical plank with an initial speed of 92 meters per second. So the question is, what is the second bullet's speed after passing through the plank? And you can also assume that the force that the plank exerts on a bullet is not dependent on the speed of the bullet. So I know that was a mouthful, but let's get into the question. So before allow you guys the time to just solve it, I'm going to sort of help us start this question out. So we have a plank of wood, right? This is sort of a plank that a bullet has passed through. So this is the bullet. And at this point, right, the V initial from this specific bullet is 153 meters per second. The V final is 130 meters per second because as the bullet went through the wood, it slowed it down to this point. Okay, so we have another situation with an identical bullet and identical plank, except the bullet in this case was traveling at a different velocity initially. And so as we can tell from the question and just the numbers that were given, work was done on the bullet by the plank. That's why it slowed down in the first case. And that's why its speed is changing for the second case. Or I'm sorry, I should say its velocity. And we are asked to find that new V final. So based off the information that we're given from the first question, the first part of the question and the second part, we can also assume that the force that the plank exerts on a bullet is not dependent on the speed of the bullet. So if we have an identical plank with the same bullet that has the same mass, which this question does, we can pretty easily find the final velocity of the second bullet given the velocities from the first bullet. So I'm going to give you guys probably around 10 minutes to do this question on your own, just to work on it individually. And the of the first bullet is equal to, so 1/2 m, because I'm not given m in this question, so that stays the same. And so it becomes 153 meters per second squared minus 1/2 m 130 meters per second and this whole thing is squared. Okay, so I'm not really left with much else mathematically that I can just kind of solve for, right? Because I'm not given m at any point in the problem. But as we'll see later, m is kind of not really relevant to us solving for our answer. But what I can do is I can remove 1/2 m, so I can kind of isolate it and leave the numbers together. So I can just factor that out, and I'm going to have 153 meters per second squared. I'm sorry, meters per second, and then the whole thing is squared. Meters per second squared minus 130 meters per second. Whole thing squared, and then surround that by parentheses because again, we did factor out that 1/2 m. And so what I'm going to do at this point is I'm just going to solve for that number on my calculator. So I'm going to pull out my calculator. I have 153 squared, which is equal to 23,409. Oh, do you know what? I'm sorry. I have the values flipped of MVF and MVI. My bad. This is 130, and this is 153. Sorry about that. Hopefully that's clear to everybody. My bad. I did flip those values around. So just, to reset that, 1/2 MVF squared minus 1/2 MVI squared, factor out the 1/2 m, and then plug in my values of VI and VF, which were up there. So my bad, I did mix those up. But anyway, moving forward, so just go on my calculator. I'm going to square 130. That's equal to 1/2 m times 16,900 meters squared per second squared minus 23,409 meters squared per second squared, because all units have to be squared. So I'm at this point and I have these numbers, but since these are in the parentheses together, I can just subtract them across, and I can just have some value sitting there rather than being stuck with these big numbers for no reason. And if I do subtract them, so I do 16,900 minus 23,409, I should be left with negative 6,509. So the total work done by this system the total work done on the bullet is equal to 1/2 m times negative 6,509. Well, at this point, if I know the work done on this bullet, and I said earlier that the work done on the second bullet has to be the same because the plank is what's doing the work on it, and the plank is identical in both situations. Well, then I know that the work done by bullet 2, so I'm going to say this is WT1 from the first, is equal to WT sub 2. I can just set what would have been this formula for this bullet equal to this value, because in the end they're going to be they should be the same because the work done on each bullet is the same by each blank. So that means negative 1/2 m times 6,509. Just multiplying out that negative sign from the parentheses. This should be equal to 1/2 MVF squared minus 1/2 MVI squared. So I have some formula, and now I just need to plug in values. If I'm looking at this, I can see off the bat that I can cancel out 1/2 m from every value on each side of the formula. So 1/2 m is now canceled out. Just divide by 1/2 and divide by m on each side. So I'm left with negative 6,509 is equal to VF squared, because that is our variable, minus 92 meters per second, quantity squared. Let me shift some stuff over to make some room. Okay, going up here now, I can say that because I'm just going to add 92 meters per second quantity squared to the other side, I can just say that negative 6,509 plus that value, meters per second squared. I can say that that is equal to VF squared. That value is equal to, so 92 squared plus negative 6,509 should be equal to 1,955. So VF squared is equal to 1,955, taking the square root of both sides. Actually, I'm sorry, let me maintain my units, 1,955. Meters squared over second squared. And just to do some kind of analysis before I solve for it, I'm taking the square root of meter squared over second squared. So, square root of that is meters over seconds. So I can already tell that my answer is going to be to have the units of meters per second. So it's kind of a hint that my answer is correct, because as we all know, velocity usually has units of meters per second. So that seems like it's correct, and I haven't even solved for a number. So I can tell that VF is equal to the square root of 1955, which is equal to 44.215. 215, but we do have to take sig figs into account. So looking back on my original question, I have 153 meters, 130 meters, and 92 meters. Well, there was multiplication done throughout this question. So I most likely have to use the one with the least amount of significant figures, which is going to end up being the 130 and the 92. So I can tell that my answer should have two sig figs. So my answer should be 44 meters per second. So the next question also has to do with work. And this one's going to be kind of a practice of making sure we understand the connection between force, distance, work, all the components of work, pretty much, which very much plays into energy, as we saw before. But in this case, we're looking more specifically at solving for work and relating it more to the integral that we've gone over, which is, work is equal to the integral between, force and distance, which is also equal to force times distance times cosine of the angle between them. But we can get into that in a sec. So what this question is asking is, there's a farmer hitches her tractor to a sled loaded with firewood and pulls it a distance of 20 meters along level ground. The total weight of the sled and load is 14,700 newtons. Remember, newtons can be a unit of weight, or it is a unit of weight. And the tractor exerts a constant 5,000 Newton force at an angle of 36.9 degrees above the horizontal. A 3,500 Newton friction force opposes the sled's motion. Find the work done by each force acting on the sled and the total work done by all forces. So there's a lot going on here, right? So, we're asked to find a bunch of different works done specifically by each individual force. And then we're also asked to find the total work done by those forces. And, we're given a lot of information. The tractor moves a distance of 20 meters. The weight of the sled and load is 14,700 newtons. And the tractor exerts a 5,000 Newton force at an angle of 36.9 degrees. And you're asked to find as well the 3,500 Newton friction force. So like I said, when it comes to finding individual forces, it is going to start off rather similar to when we're doing our like Newton's forces equations, right? Or like we have a wedge and multiple boxes and things of that nature. And what I mean by that is, the first thing I'm going to do is I'm going to draw a free body diagram. That's the first thing I'm going to do. So I'm going to draw a free body diagram for the load, because that is what seems to make the most sense to me, because that's what's actually moving, and that's kind of what we care about. And that's, that's kind of where all the weight is coming from. So I can tell from the question, I have a 3,500 Newton friction force that opposes the sled's motion. Well, even just based off looking at the diagram, I can tell that the sled is moving towards the right. So in my case, the friction has to point towards the left because it's opposing motion. So this is a 3,500 Newton force right here. So friction, I'm going to call it kinetic friction because it is moving, so it's kinetic. F sub k. I also have, I'm sorry, I didn't mean to draw that. I also have this angled force right here, and that is the tractor pulling on the sled. So that is a 5,000 Newton force. So I'm just going to call this, F sub t because it's from the tractor. That's equal to 5,000 Newtons. And it's acting at an angle of 36.9 degrees. Okay. And then I have the weight of the sled, which I'm told in the question is the total weight of the sled and the load is 14,700 Newtons. Okay, so that's equal to W. And then I have the normal force, which in this case is equal to W. Okay, so when it comes to finding individual work done by each force, I have the formula F times distance times cosine of the angle between them. That's what work is equal to for each force. So pretty much at this point, I just have to start plugging numbers in. So the work done by friction is equal to 3,500 times the distance traveled, which in this case is 20 meters. Normal wouldn't equal weight. Is there a reason why it wouldn't equal the weight? The tractor itself is not necessarily pulling up. It's more so that the tractor is just at an angle like that. I mean, it's still moving horizontally, strictly. It's not pulling it up. So there is no, the normal force is still equal to weight. It's moving it horizontally still. And it does say it's moving it along ground level in the question. So for this case, the normal weight is equal to the normal force is equal to the weight. Yeah, so hopefully that clears up. It's still moving horizontally. Although it is, at an angle, it's still not moving upward. Okay, so getting back into it. So we're solving for the work done by friction. So the work done by friction is equal to 3,500, which is, 3,500 Newtons, which is the force done by friction. And we need to multiply that by 20 because it is moving 20 meters as stated in the question above. Okay, and there's also some cosine angle. Well, in this case, it's going to be cosine of 180 degrees. And the reason it's like that is because the tractor is pulling the load this way. And so if I can imagine an imaginary line here, right? This is just movement. And friction is facing this way. That means there's a 180-degree difference between the direction of friction and the direction of the movement of the tractor. So that's 180 degrees, which is cosine of 180, which changes our answer significantly. It makes work negative in this case. So this is going to be equal to 3,500 Newtons times 20 meters times -1, because again, cosine of 180 is -1. And 3,500 times 20, I know 35 times 2 is 70. So, and then I have to add the 3 zeros from the rest. So it should be 70 kilojoules times -1. So it's equal to 70 kilojoules, which is also 70,000 joules times -1. So the work done by friction is -70 kilojoules. Okay, well, let's look at the other forces that I have to do now. I have to do the force due to tension, which is, from the tractor. So W sub T. Focusing back up, now that we're solving for work due to tension, this is equal to force due to tension times distance times cosine of that angle. And that's equal to this force over here, which was 5,000 Newtons. 5,000 Newtons times distance of 20 meters times cosine of 36.9, because that is the angle this makes over here. This angle is 36.9. So that's the cosine of the angle that it makes with distance, which is going horizontally to the right. So cosine 36.9. So I know 5,000 times 20 should be just, like, that should just be 100,000, I believe, or 10,000, my bad. Or yeah, it should be 100,000. Should be 100,000. 5,000 times 20 should be 100,000 times cosine of 36.9. So 10,000 or 100,000, my bad. 100,000 times cosine 36.9, which is equal to 0.799. I'm just going to round that up to 8. So it should be times 0.8. So this is equal to 80 kilojoules, the work due to tension. Okay, and so now let's take a look at why the normal force and the weight, even though despite the fact that you could solve for each, again, because the normal force is not equal to weight, like we said before, why it's still kind of insignificant, right? We can kind of just tell, it's not moving, so there's no work being done in the y direction because it's not moving in the y direction. So we can just say that. But if we want to show that mathematically, right? If W is equal to FD cosine of theta, well, one, it's not moving in the y direction, so that's already 0. And also the angle between the y direction and the movement of the object is 90 degrees, which is cosine of 90 degrees. So that's also 0. So double, 0 times any value, doesn't really matter. It's still 0. So it does not really affect our answer in any way. And it doesn't affect our tension because we just care about the work due to tension. We're not caring about the components of the work due to tension. We're just caring about straight up about the work due to tension. And all that matters in that case is the force done by tension, or the tension force. So we have our two values, and everything else is pretty much, 0. So it doesn't really affect us in any way for this case. And so what we can do now is there are two ways to solve for the total force. We could just add up all these values, right? We could do work total is equal to the work due to friction plus work due to the normal force plus the work due to weight plus the work due to tension. You could just add them up. Well, this is 0 and this is 0 because it's the normal force and work. So 0 and 0. And then the work due to friction is negative 70 kilojoules, I'm sorry. And then the work due to tension is 80 kilojoules. So we can tell now that the total work done is 10 kilojoules. Okay, so that's one method of doing it, just add up all the values of work. Or we could just do it a kind of a easier way. We already know that work total is due to just force times distance times, again, cosine of the angle between them. And we know that if we go back to our original question, we can tell from the information that we're given that it travels 20 meters. So we already know what our distance is, and we know what the total force is done by the entire system. Again, we can kind of just add them and subtract them. And so in that case, we could take into account the normal and work, which again, this might be a little bit easier because we already have the formulas memorized in this case. But in that case, you do have to solve for force. So, it does make it a little tougher. So that would, again, and then we would have to take into account, solving for normal force and solving for weight. But in our case, we could also, for this question, just add them across, which is a lot easier. At least I think it's a lot easier to just add the values that were given. But it seems like a lot of us did just solve for that force using the component form, so we can go ahead and do that as well. So for this case, we have to solve for the forces in the x direction, which is equal to the force of tension times, cosine of that angle theta for the x direction, because again, right, it's adjacent over hypotenuse. So cosine of 36.9. And then we would also have to subtract friction because that's also moving in the x direction. And this should all be equal to, let me move this down. So the sum of forces in the x direction should be equal to 5,000 newtons, right? Because that's the total weight of the sled that we're given by the question. Oh, I'm sorry, that's the work done, that's the force done by the tractor through the, the chain that's connecting them, times cosine of 36.9. We're just moving our values across, minus the friction force, which was all in the x direction, so it's only 3,500. And if you solve that across, you should get about 500 newtons. So I know it's a little weird. Usually we're used to having to solve for something, but in this case, we're just subtracting and adding across. It's a little bit easier. And like it looks like a lot of you did. So now I'm starting to understand why a lot of us were so focused on finding that value. I kind of assumed the route that you would take was this way. But it is great that you took this way and that you were still able to practice your forces. So that's why I kind of said that the forces don't matter too much, because I was thinking more of solving it using this method. And I hadn't realized that a lot of us would end up solving it using this method. But that's great that you took maybe sort of the harder way and you put a little bit more work in and kind of practice your algebra skills a lot more. So that is the reason why I was kind of not so focused on it earlier in the session. But getting back into it, if we want to solve for the y direction, it's pretty similar. It's force of tension times sine of that angle now, minus weight, which we are given, plus the normal force, because that's also acting in the y direction. And so this should be 5,000 times sine 36.9 minus weight, which is 14,700. And if you had solved for normal force earlier, you would be able to just plug that in. And we can tell here that since this is equal to 0, sorry, let me clean this up a little bit. You would have to add n here. In our case, it doesn't really matter because the forces in the y direction don't really help us too much. We're kind of just doing that just to do that. So this would help you solve for n, but again, it doesn't really help us too much in the question. But generally, it's kind of good practice to still lay out the forces in the y direction anyway, regardless of whether or not you're going to use them. So from here, we can just plug that 500 that we solved for earlier into our question. So 500 times distance of 20 meters, 500 newtons times distance of 20 meters, times cosine of 36.9, because that is the angle between them. Oh, I'm sorry, not cosine 39, cosine of 0, because that is both the x direction, that's where the force is pushing it because it's moving horizontally, and the distance is, moving that way as well. So they're going in the same direction, basically. So cosine of 0, well, cosine of 0 is 1. So 500 times 20 is 10,000, which is 10 kJ, which is the same answer as we got from here. So are there any questions about that? I know that got a little complicated towards the end, but should be kind of clear at this point. So are there any questions about this moving forward? Is there anything confusing at all about the solution to this problem? Are there any questions about anything in general? Again, if you don't have any questions, the session's kind of over at this point. You can feel free to go, but I appreciate everyone coming and participating and everyone sending their answers and, correcting me when I made a mistake as well. But if there are no questions, you can feel free to go. Be on the lookout. Hopefully I can have this edited soon and send out the YouTube link to you sooner rather than later. But if not, you can feel free to leave. Appreciate you guys coming on a Sunday and taking time out of your schedules to come to the SI session. And remember, the next session's on Monday at 1 p.m. On an exam, depending on your sig figs, I'd probably just leave it in joules, to be honest with you. I kind of just left it in kilojoules just to make it neater. But I don't think you would be affected one way or the other as long as your sig figs were correct. But maybe just leave it in joules just for the sake of just keeping it clear. But as long as your sig figs are correct, I don't see it mattering one way or another. Yep, thank you. Again, feel free to leave if you don't have any questions. Yep, I appreciate you guys coming. Thank you.